Hello students, we have discussed about vector atom model, and in that we have seen that the atom model is described in terms of some vectors like orbital angular momentum, um, spin angular momentum vector, and then total angular momentum vectors, which recur, and all of them were quantized, and some quantum numbers were involved with those vectors, which are given by L, S, J. Okay, and S, P, D, F represents the different values of L, the letters representing different values of L, and the small letters are used to represent the state of a electron, while the capital letters are used to represent the state of an atom. So how do you obtain the state of an atom? That is by combining one or combining the corresponding vectors. So that combining can be done in a different way. And for mentioning the state of an electron, not all the quantum numbers need to be mentioned. Only 4 quantum numbers is enough to represent the state of an electron in an atom completely, and those are given by principal quantum number N, then orbital quantum number L, then magnetic orbital quantum number ML, and magnetic spin quantum number MS. So as we mentioned earlier, in order to get the total state of the atom, the vectors involved has to be added up. So it will depend upon what is the interaction or coupling between the vectors, that is orbital angular momentum vector and between the spin angular momentum vectors. So here we have seen that there are 2 coupling schemes possible. One is called LS coupling scheme, where we have seen the orbital angular momentum of each electron will be added up to get a cumulative orbital angular momentum, as well as the spin angular momentum of each electron will be added up to get the total spin angular momentum vector, and the total angular momentum vector will then be the sum of the total orbital angular momentum and the total spin angular momentum vector, and which was the normal way of coupling. And all of these we have seen the value of J will depend upon S, whether it is integer or half integers will depend upon S, because L is already an integer. So the effect will be due to the presence of half integers in spin quantum number. And the next coupling scheme is JJ coupling, and from the name itself, J represents, small j represents the combination of orbital angular momentum and spin angular momentum vectors for a single electron. So initially it will be added up for a single electron, and it will be proceeded with all other electrons, and the cumulative total angular momentum will be sum of all these small g's. It is because the interaction between orbital angular momentum and spin angular momentum is stronger than that among the orbital momentum alone or spin momentum alone. So here you can see this is for a single electron, and it will be proceeded with for the other electron also, and correspondingly that for an atom it will be just the sum of all the angular momentum corresponding to each electrons. So vectorially, in a vector representation, here you can see initially, if it is a 2 electron system, initially S1 and S2, the resultant will be given by capital S, that is vectorial addition will give capital S. Similarly, for L1 and L2, the vectorial addition will give the resultant along capital L, and this S and L will be vectorially added to get the total angular momentum vector. That is how vectorially we will be obtaining the total value J. Similarly, in J coupling scheme, we have mentioned that the addition will take place between spin and orbital angular momentum of an individual electron. Here you can see between L1 and S1, the addition will take place, and resultant vector will be given by J1, and between S2 and L2, vector addition will give a resultant vector J2 along this direction, and corresponding capital J will be sum of this J2 and J1 vector sum, which will be a resultant vector along this direction, and that is how we got it. Okay. So all these resultant vectors, capital L, capital S, capital J, represents the total with respect to many number of electrons, right? That means it represents the state of an atom. And according to the quantum theory, all these L, S and J must be quantized both in magnitude and direction. Not all the values are possible, and the quantization is given by number of permitted values are given by 2L plus 1 values will be there, and with respect to S there will be 2S plus 1, and with respect to total angular momentum it would be 2J plus 1. Okay, and this 2S plus 1 is called multiplicity in terms of spin. Okay. Now let us see how an electron is represented, and what is called electron configuration. And we know that for an orbit n, there would be n subshells, isn't it? That is, for the first orbit there would be how many subshell? One subshell, which is L equal to 0. For n equal to 1, for the second orbit, how many subshells will be there? 2 subshells will be there, which are they? L equal to 0 and L equal to 1. Okay, so here it is given. If it is n, there would be n number of subshells starting from 0 up to n minus 1. So total of n subshells will be there, and 0 is named as S subshell, 1 L equal to 1 is named as P subshell, 2 as D subshell, 3 as F subshell, 4 as G subshell, 5 as H subshell, and so on. So an electron in any orbit n and with a subshell value L will be written as n followed by the letter representing the L value. For example, if you are considering an electron in second orbit and in S subshell, it will be represented as n is 2. So 2, and the letter representing L value is S. So 2s electron. And hence electronic configuration of an atom means that how these electrons are distributed in various subshells around the nucleus of the atom. As we have mentioned, Bohr has mentioned that electron will be present in a certain specific number of orbits, but he has not mentioned about how it will be arranged in a particular orbit. In the vector atom model, it is mentioned that using the electronic configuration, you can mention how the electrons are distributed in various subshells in a particular orbit itself. Okay. So the point to be considered before going into electronic configuration or writing the electronic configuration is that for any orbit n, the total electron that could be accommodated is 2n square. Okay, so if it is n equal to 1, that is first orbit, what would be the total number of electrons occupied? It would be 2 into 1 square is 1. So how much? It can occupy 2 electrons. Okay, and if it is equal to n equal to 2, that is second orbit, how many number of electrons could be occupied? 2 into 2 square. 2 square is 4, which means 8 number of electrons could be occupied. Okay, so corresponding to the n value, there would be 2n square electrons in that particular orbit. So taking that point in mind, let us write down the electronic configuration in different atoms. So let us take the simplest one, hydrogen, and Z is given as 1. What do you mean by Z? It is the atomic number. And what does atomic number means? It is the number of electrons in an atom. For hydrogen, the number of electron is 1. Okay, so we need to represent 1 electron among the orbit. So it will prefer the ground state. Ground state means it is the lowest possible state electron will be occupying. So here you have n would be 1, L equal to 0, and maximum value is given by what? What is a maximum means? It is the number of electron possible for n equal to 1 orbit. As we have seen, it can occupy up to 2 electrons. But there are no 2 electrons in hydrogen, only 1 electron is to be represented, isn't it? So you can represent it as 1, which means first orbit. S represents the value of L, and only 1 electron is involved. So that is written as a superscript. So it is 1s1. So is it complete now? No, because the orbit can accommodate one more electron to become complete, right? So hydrogen will always try to make it complete, okay, by chemically reacting with other atoms. And hence we can mention that based on electronic configuration, we can see whether an atom is chemically active or not. So for hydrogen it is not complete, and hence it is chemically active. Now let us see helium. Helium has atomic number 2, which means the number of electrons in helium is 2. So corresponding to that, we can choose the lowest orbit, which is n equal to 1 first orbit, and the possible values of L is, again one subshell is possible, which is that 0. So and the maximum number is again given by 2 into 1, which is 2 electrons. So here 2 electrons are already there in helium, so we can represent it as 1s square. Okay, but there is a box is given. What does that mean? It means the electron is locked within the subshell. What does that mean? Because the because the subshells are completely filled. So there is no possibility for helium to react with others or chemically become active, and hence helium is said to be inert. And this is the case with all the noble gases. Where it behaves as inert. Why? Because the subshells or the shells in those atoms are all filled. So they will be locked inside the subshells. Okay. Similarly, let us consider another atom, lithium, with atomic number 3. So what are the possibility? You can have n equal to 1, and corresponding to that, one subshell is given by L equal to 0, and the maximum value is given by 2. But you have 3 electrons to be represented. So one more orbit to be considered, n equal to 2. So the possibilities are for subshells are 2 subshells are possible. Which are they? L equal to 0 and L equal to 1. And what will be the maximum? Maximum is given by 2n square. So 2 into 4, which is equal to 8 electrons can be occupied or accommodated in the second orbit. So considering these in mind, let us write down the electronic configuration. So it would be 1. Initially the lowest orbit will be filled up. So 1 s square. Okay, 1 s2. 1 s2 na paraya. 1 s2 and one more electron to be represented, so that will be going into the second orbit. So 2, lowest one is s, 2 s 1. Okay, this is the electronic configuration of lithium. And here you can see it is not completely filled because you can accommodate up to 8 electron. Only 1 electron has been accommodated, which means the lithium will also be chemically active, and similar to the hydrogen, it also have 1 electron in the outermost shell, isn't it? So lithium will be coming in the hydrogen family, or which is called alkali metal family with 1 valence electron. So here you can see that the chemical nature of the atom will depend upon what is the number of electron in the outermost shell, which is called valence electron. So the number of valence electron will decide what will be the chemical or optical property of an atom. We can see similar electronic configuration for other atom also. So let us see for oxygen with atomic number 8. So 8 electron has to be represented. So starting with the lowest orbit, first orbit, the subshell possible is 0. One subshell is the 0, which is the values represented as S, and the maximum possibility is given by 2n square. So 2 electrons could be occupied in first orbit. We have 6 more to be represented. So we'll again go for the next orbit. Next highest orbit is second orbit. So for 2, n equal to 2, there will be 2 subshells which are S, and L equal to 0, which is S, and L equal to 1, which is P. And the maximum number is again given by 2 into 2 square, which is 8 electrons. Okay, so let us represent oxygen. So starting with the first orbit, 1 s2. Okay, 1 s2, followed by the second orbit, 2 s2. Okay, then followed by p orbit, p subshell. So it belongs to second orbit. So 2p. How many number of electrons are again remaining? 4 has been already been mentioned. So you have 4 more to be mentioned. So it is 2p4. So is it complete? In the second orbit, it has 4 plus 2, 6 electrons have been accommodated in the second orbit. Is it complete? No. It has a possibility of accommodating 8 electrons. So because of the incompleteness, the oxygen will be chemically active. Now let us see about neon. Neon is with the atomic number 10. So again, starting with the lowest orbit, first orbit can have one subshell, which is S, and it can accommodate up to 2 electrons. So again we need to represent 8 electrons. So we'll move on to the next highest orbit, which is 2. Then the number of subshell possible is 2, which is L equal to 0 represented as S, and L equal to 1 represented as P. So 2 orbits will be enough, karanam 2 plus 8 is 10. So you'll get the exact atomic number of neon. So let us represent it. So it is starting with first orbit, 1 s2, then 2 s2, then 2 p, remaining is 6. So this is how it is represented, and it is an inert one, And here you can represent in a box, which again shows that it is a complete subshell or orbit. All the electrons are locked, completely filled inside the orbit, which means it is locked in the orbit, and hence it need not react with others to make it complete. So neon atom will be inert. Okay, so coming under helium. Similarly, you have sodium. So in sodium, atomic number is 11. So you'll require next third orbit also to represent. 10 will be represented using first and second orbit, and one more electron to be represented. So we will require third orbit. So n equal to 3. There are 3 subshells will be possible: S, P, and D. And what will be the maximum? 2 into 3 square, that is 2 into 9, which is 18 electron can be accommodated in third orbit. And how would we do? So 10 has been mentioned as 1s2, 2s2, 2p6. Okay, and remaining 1 electron will be given to the next highest, which is the next highest? 3s1. Okay, again you can see that up to the second orbit is completely locked up, and only one valence electron is there, similar to the hydrogen. So again it will be a chemically active. Okay, so the points inferred from the electronic configuration is that chemical and optical property of any atom will depend upon outer or valence electrons, the number of valence electrons. So electrons in the closed inner orbit do not take part in the emission of spectral lines. They are actually locked inside. We have shown in a box. It is because it was completely filled. And so inner orbit electron will not take part in the emission of spectral lines. Now you have, based on this, you have two kind of spectra. One is a one electron spectra, and another is many electron spectra. So the atoms will be showing spectra as one electron spectra or a many electron spectra. Let us see what is one electron spectra. So here you can see that we have already seen that valence electron in hydrogen, lithium, sodium all has been 1. So those metals are called alkali metals, which has single valence electron, okay, in the outermost shell. So that is outside the completely filled subshell, it has a single valence electron. So while in the case of many electron spectra, instead of single, there will be more than one valence electron outside the completely filled subshells, and hence the name one electron spectra and many electron spectra respectively. So in the case of one electron spectra, it is the case similar to a hydrogen atom. Hydrogen also had one electron, so it would be a similar spectrum. So it is called hydrogen like spectra. So the one electron spectra will be simpler one, which would be considered as a hydrogen like spectra. Example, atoms in the alkali metal family, which is lithium, sodium, potassium, etc. And in many electron system, the pattern is like that. A similar spectrum will be obtained for atoms with similar number of valence electron. That is, if there are 2 valence electron for some atoms, those atoms will be showing similar spectrum. If there are 3 valence electrons, those atoms will show similar spectrum. So here an example is given for the second group element, which is called alkaline earth metals. It is magnesium, calcium, and so on. It has 2 electron in the as the valence electron. So the spectrum will be called as 2 electron system. They will have similar spectrum. Now before going into how a spectrum is obtained, we need to know how do we represent a state. Okay, state of an atom is represented using what is the letter for L value, cumulative L value, capital L, followed by as a subscript J value will be written, and onto the left as superscript multiplicity in terms of spin 2s plus 1 will be written. Okay, for example, if for a state with L equal to 1 and S equal to half, let us write down the spectral term. So such an atom will be such a state of an atom will be represented by considering the letter for L value. L is 1, so the letter representing 1 L equal to 1 is P. And what is multiplicity? 2s plus 1, 2 into half plus 1, which is 2. And which are the possible values of J? J can be added as L plus S or L minus S. So the values can be 3 by 2 or 1 by 2. So based on this, you can write the spectral notation as letter for L, that is P, and as subscript you have J value, which is 3 by 2, and as superscript you have multiplicity, which is 2. Similarly here you can write this 2p half, and it is read as doublet p 3 halves. Well, this is read as doublet p half. Okay, that is how we call these state. Okay, now for considering the transitions, not all the transitions are allowed. There are some rules are involved, which is called selection rule and intensity rule, and that will be taken and in the next class, where we will be seeing how to actually obtain the fine structure of H alpha lines. So thank you, students.